Hey, what's up, guys? This is Cheng here again. So this time, today's daily challenge problem number 1268, search suggestions system, right? So you're given like an array of strings, products, and a string search word. So we want to design a system that suggests at most 3 product names from the products after each character of search word is typed, right? So obviously, the search word should have the result, the suggested products should have like common prefix with a search word, right? And if there are like more than 3 products with a prefix, we return the 3 lexicographically minimum products, right? And we need to return the list of lists where the of the suggested products after each character of search word is typed, right? So for example, so I think this one it's just like similar as like a Google search, right? Basically, every time if you search like a word in the Google, every time when you type in the word, it will give you some suggestion along the way, right? So for example, so this is the products we have, right? And then the search word is mouse. So which means so at the first time we have a search word is M, right? So for M we have like this kind of 3 words, right? Second time we have M and O, right? Typed in there. And then we have some other like search word. And then this next one is MOU, right? So when it comes to MOU, we only have like two suggested products, right? And then MOUS and then MOUSE. In the end, that's everything we have, right? So yeah, I mean, obviously, if there's nothing matched, we simply return like empty string or empty list, right? So here are some constraints we have. So the total product is like 2 times 10 to the power of 4, and the word length is 1000, right? And all characters are lower letters. So this one, obviously, the first solution will be the prefix tree, right? So basically, we simply just build a prefix tree using this kind of like all the products, right? And then we insert all the words into the prefix tree, and then uh, after that we basically we'll loop through all the prefix, right, from the search word. We loop through mo, mou, and so on and so forth, and we use each of the prefix, and then we do a DFS search, right, from the prefix tree, and then we'll get all the uh, all the possible words, right, who have the same prefix, and then we do a sort, and then we return the first one after sorting, right? So that's the first one. And yeah, and we'll implement that. And actually, there's another solution for this one, which will be using the binary search. But let's try to code that first one, right, which is the prefix tree. So I prefer to create a separate tree node class, right, to store everything I need into the prefix tree node. So this one we have the children, right? The children will be like dictionary, right? And then we have this word equals to false, right? So here, I mean, um, we can either store the word string or not, because because since we need to return the actual string, the actual word itself, while we're building like this word here, let's say we have uh, A, B, and C, right? So at the C here, we can store A, B, C, or we don't have to store it, because I store it just for the sake of code will be simpler. Because if we don't store it, actually, while we're building like this kind of like DFS here, we can just concatenate each letters along the way. So in the end, when there's no children, right? We simply we can also get this ABC, right? By storing this ABC along in at each of the leaf node, the space complexity will be a little bit high, right? But I'll just stick with this one, since that's how I implement this, right? And so once we have that, yeah, we can uh, we we can also create like a separate try class, or we can just put everything into this like one solution, right? I think we can just put everything into the solution here. So we have a root, right? Root will be the tree node, right? And then we need to have two functions. First one is add a word, right? It's going to be the word. So the current one is going to be the root, right? And then for C in word, if C not in the node dot children, right? We do a node dot children dot C equals to a tree node, right? That's how we implement the prefix tree. And then we have node equal. And then we move the node forward to the next one. It's gonna be the children dot C. So in the end, we can have like node dot is word, right? Not node, sorry, current. Current equals to true, and then the current dot word string equals to the word, right? So that's how we add the word. Yeah. And then for the search, right? So we have a search word. So for search word, all we need is a prefix, right? So we have a prefix. So the first thing is that we just need to do the current is also, we start from the root, right? And then we find all the nodes, right? Actually, we find the nodes that is the end of the prefix, right? Because we need to consume all the prefix, and then from here onward, we can just gather all the leaf nodes that has the same prefix. That's why we need to start from the root, and then so for C, similar to the add word function in the prefix, right? We have this one. So if C in node in current dot children, then we keep moving forward. So current will be the current dot children dot C, right? Else, if we cannot find any letters from in the prefix tree exist in the any letter in the prefix string in the prefix tree, and then we know, okay, there's no valid suggestion, which means we can simply return an empty list, right? Otherwise, if we have find all the letters inside the prefix, and then we can do a DFS starting from here, right? Yeah, because here, if we do a DFS from the current one, so basically this means that, let's say if we have A, B, C, right? Again, A, B, and C. So the prefix is this, right? A, B, and C. So after A, B, and C, right? After this for loop here, the current one is pointing to this one, right? Because that's how we do the current dot children, right? And starting from here, we could have different like letters, right? We have a D, E, F, or something like this, right? So it could be and then a D, B, it doesn't really matter, right? So basically starting from here, we want to find all the leaf nodes, right? Starting the leaf node who is a parent, who is who is the parent node starting from here. That's why we have to scatter it. We have to scatter it around. We have scatter it, and then we do a DFS starting from here. And yeah, and after the DFS, right? After the DFS here, we have a candidate, right? From this DFS, and then we do a sort, right? We do a candidates dot sort, and we do a return candidates, the first three, right? So that's how we do this thing here. And in terms of the DFS, right? So let's just define that DFS here. So we have a DFS, and it's going to be the node, I'm assuming, right? And if the node is word, right? We have find a leaf node. Not actually, it's not a leaf node. I think my mistake. It could be also like right in the middle, right? Because so we have some node, right? This one could be a valid ladder, and this one could also be a valid ladder. That's why so it shouldn't be a leaf node. Basically, any node who has this flag equals to true, right? Yeah. So which means that actually we should not return from here. We should just keep doing, because if this one is a word, maybe the next one is also a word, right? Maybe there's another child, right? That's why I see. So in this case, yeah, let's do this. Okay, I'm going to move this DFS inside the search word here, okay? Because here I'm going to have like an answer, right? I mean, so in this case, the candidate should be at the beginning. It will be equal to this empty, okay? And so inside this DFS, okay, inside this DFS, whenever the word is true, and then we just candidates, right? We append this candidates with the current with the node dot word string, right? Since we also store the word along with this flag along with the node, okay. And then for child in node dot children, right? With DFS, we do a DFS of the node dot children dot child, right? It's simple DFS. We just DFS traverse all the nodes after this current nodes, and after this one we have candidates, right? And then we just do a sort, and then we do return. Yeah, so that's the basic. That's all the helper functions here, And when it comes to the main logic, we simply just do so do a first for word, right? In products, we first build the prefix tree, right? So we have add word, right? Word, yeah, add a word, and we have answer, right? And then for each of the search string, right? So we have this prefix, right? Empty, right? So for C in search word, right? So prefix plus C, right? And then we do a search. So the result is going to be simply just append, right? Append this kind of search Oh, this is they're the same actually. Let's do add and search in this case, since we have the same name here as a variable. Yeah. So I think here we'll be just add and search, right? So we search this prefix. Yeah, and we return the answer. Yeah, I think that's it. So let's run the code. Yeah, accepted. Yeah, cool. So pass, right? And yeah, nothing fancy, right? Just a very classic prefix tree implementation. So for the time and space complexity, I mean, so we have word here, right? So to build the prefix tree, we need to basically we need to enumerate, traverse all the words, and for each word we have to do another for loop to traverse each character. So to build the prefix tree, we have O of so I can use a big M here, right? So big M means that this is the total characters among all the products. And then to do a search, right? So to do a search, the search word is it's like 1,000, right? Because the search word is like it should be smaller than each of the products, right? Not smaller actually. It's their length here, the product length, and okay. So here's a search word is 1,000, right? And then for each of the prefix, we do a search. So the time complexity first do a search is so first we'll do a for loop here, right? To find the last letter, the last node after doing this kind of prefix, and then from there onwards we're gonna do a DFS, right? So the DFS here, the DFS, you know, the worst case scenario, we'll basically traverse all the possible nodes in the in this tree, right? So the possible nodes in the tree will be the number of the products. Uh, yeah. So for this one, so the first one we have 1,000, but inside of the search here, right? We also need to do a like for loop up here. So it's gonna be a like 1,000 times 1,000, right? And then in terms of the DFS, right? I mean, after this one, we have DFS, and so the DFS can the number of DFS is also uh, up to the number bounded dominated by the number of products. So that's why the total time complexity for this one is gonna be O of m, right? I would say this basically O of m plus this. This is O of m square. Yeah, and since this one is like 1,000, and so this big M is right here. It's 10 times 10 to the power of 4. And this one is 10 to the power of 6. Yeah, so actually, so basically this one is dominated by this kind of M square. So that's the total time complexity for the first solution, right? And yeah, and for the second one, right? I mean, for the second solution, like I said, we can use binary search to solve this problem. And how can we do it? Right. So basically, since we have a prefix, right? So we have prefix, and then we have a bunch of words that we want to search on. you know. So for example, if we have like this kind of BAG, right? So if we have like this ABC, you know, ABD, right? And ABE, ABF, okay? And if our search string is like this is AB, okay? And let's say we have a AAA, AAB, AAC, okay? Right? So if this is the word, and if we try to search the prefix, is the prefix, right? It's AB. So what are we expecting to get? Right? So we're expecting to get ABC, ABD, and ABE, right? And why is that? Okay, so let's assume if we sort, right? If we sort these products from the smallest to the biggest, and as we can see that, you know, our starting point of our answer has to be at least has to be greater than this AB. It's obvious, right? Because you know, since we need to get the prefix, right? So which means that you know it has to be either equal or greater than the current one. Because let's say for example it's AAB, right? You know, this one I would definitely smaller than the AB. So which means you know if we do a binary search uh, on the sorted products and we use this when we search this this prefix, we'll get an index. So the index will be what? So the index will be the first letter. Sorry, will be the first word who is greater than this AB. Okay, and then all we need to do is that let's say if we have an index. So all we need to do is that we just need to check the next three words from this index if they have a prefix of this AB, right? And why we only need to check the next three one? Because obviously this one, you know, we have ABC, ABD, and ABE. That's why these three are the answer. You know, let's say if the next one is like this, if this one is like it's ACE, right? And this is it's ACD. Remember, we have already sorted these words, right? In this case, you know, okay, so we're starting from ABC and ABD, right? And the ABC is right. ABD is also right, right? It's also has a prefix, but the ACE does not have. Does not have like prefix. So which means that you know, if this one doesn't have a prefix of AB, then it means that the next one will definitely not have the prefix as AB because again, right? Because the number can only be increasing. Sorry, not the string can only will only be becoming bigger and bigger. That's why you know for this one, if it has like A and C, the next one will also have like A and C, and this one can only become bigger. That's why you know we only need to check the next three uh, strings if they are like if they have the prefix or not. Right. So I think that's it. And let me comment out this long code here, and we can write some pretty neat code here. So all we need to do is that, you know, like I said, we need to do a products.sort, right? And then, oops. And then we have the answer like this one. And then for, again, we need a prefix, right? So similar for prefix equals this one. For C in search word prefix plus C. And then we have index. So we do index of bisect, right, left. So we search from the sorted products and we search this prefix. And from this index, right, we just do this. We can just simply do this answer.append. I'll just write like a combined code here. Or let's just do this for I in range of 3. Okay. So if if the products okay. So if the products I plus offset, okay, starts with the prefix, and then we know the so this is the answer. Here we need like another list to store the current answer, right? Let's use the let's use suggestions. Okay, and then we do suggestions, right? Dot append this this product, right? And then the answer dot append the suggestions, and then return the answer. Yeah, yeah, index here. Okay. Yeah. So I see. So I think here I think I made a mistake here. I guess I can do this. So we have instead of doing this one, we can just do a slicing of the products here, right? Yeah, I think this one's better. We do slicing from the product from the index to the index plus 3. Okay. So now I just need to do this p here. Okay, and I just add this p here. Because with the slicing here, the slicing will take care of the if this index plus 3 has reached is bigger than the length, then it will just simply ignore those things. Yeah, so now it works. So submit. Yeah, so as you guys can see, this one is much faster, than the prefix tree, because I think it's because the sorting here we have what we have. Let's say this is n, right? So this is n log n, right? N log n, and we have this kind of am here, maybe. So the word is like this is am, let's say. Well, actually they're the same, but this one is am. So am. So binary search. This one is log n, right? Because the length of the product is log n. So this one is log n, and then yeah, and then we have this kind of like this one is O of 1 because it's a only 3 for loop here, but we have this kind of p start with, and this one is also like m, right? Because we need to find the prefix from this word here. So I would say this one is also like m square, right? So I think this one is kind of m squared times log n. So because this one will dominate the overall time complexity. Yeah, I think it's faster than the previous one, right? Yeah, so I think that's pretty much everything I want to talk about for this problem. And yeah, I'll just stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.